Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Here we are back at the technical deep dive of the Hawkeye disc version. Now the first thing to note here is that this boot menu screen actually has an extra message. It says this game incorporates dodgy load, and this text is with a black background, so you're not going to see it. I'm just going to hunt through the memory here, see if there's anything different. Not really. We can see that where the code is executing quite high up in C000, I think, onwards. Looks like it. We can see the speed of the disk loader here. When we have a look at the disk loader, we'll be able to see, I think, that it's a 1-bit disk loader with a handshake. This is not surprising because most of the disk loading is actually done with the screen enabled. So we can see here that there's quite a lot of memory being read in green up at the beginning of memory. There's a lot of writes in yellow visible at the end of memory. So if we have a look at the bitmaps, we can see, of course, that there are some bitmaps. We can see that there's quite a lot of what looks like bitmap data. Again, unsurprising if it's reading the bitmap data from the animation frames stored in lower memory and then writing them into the bitmap at the end of memory, then this is in alignment with the pattern that we can see in the ICU memory debug view there. If we have a look for sprites, we can see what parts of the screen are animating sprites. We've got press space. Surprisingly, press space is using sprites, and it's got like a raster bar color effect in the sprite colors. Interesting, and the text, of course, in the monitor is also animating. We can see that the little animating vertical bar graph as well is also an animating sprite. We can see, of course, that the text is being written not as raster bar characters actually, but as a bitmap font with the color graduation fill actually within the font itself. I actually like the idea behind this screen. I think it tries to set the backstory and the tone to the game. I just think it could have done with some audio. You know, there's a lot of memory free here. Maybe there could have been some synthesized speech or something like that. That would have been nice. Or just some mood-setting music would have also been great. Just having a look through the memory, I can see this kind of pattern in memory. I'm thinking that this might be animation data. We can test that hypothesis by perhaps clearing the memory or setting portions of that memory and then seeing if the animation then behaves differently. We could do that. Let's have a quick look at what is in the monster show memory. We can see some text. Actually, down in the bottom screens I can see file names, save file, disk error, and some other human readable text. There's quite a lot of memory that looks to be free. There seems to be a basic program here, or at least the start of a basic program at roughly 4800 in hex. We can have a look at that later on. Bottom right hand corner of the text screen I can see demo 2 800 in hex 0800 right in the bottom right hand corner there. I can also see what looks like PC IRQ PP AC XRYR SP NV BDIC. This looks like a machine code monitor register view. This might indicate that there is a machine code monitor or parts of a machine code monitor left in memory, perhaps. Blank memory, perhaps music data. It looked like a music routine updating its internal registers. It had that kind of pattern to it. And that's the thing, when you're looking at the text screens, the memory view basically, like this, you kind of get a feeling by looking at how the data changes you get a feeling about what it's doing, because you have the contextual information about what is going on the screen as well, so you kind of can intuit about what code is running. So we're having a little look here at 5C00. in terms of memory. We can see the text, demo 2, we can see the PC IRQ PP DRACXRYR, the machine code monitor register view. Maybe this code was originally called demo 2, demo II, with a star for matching the file name perhaps. So we're just having a little look here at the disassembly. We can see that there's loadx or a JSR. I don't think this is code. I think this is this might be data that looks like code. But we're trying to find the start of this string now in memory, and the start of the string looks like it is around about 5F3 something, 3B perhaps. I mean, that's the start of where it says PC, but there's some preceding spaces, the 20 in hex characters. So we're going to look through the whole of memory for something that references in the low and high byte order the monitor's text, or what we think is the machine code monitor text. Okay, so we're gradually going backwards from what the address for PC is. And we keep on going backwards. We can find one address out of the whole Commodore 64's memory currently loaded. We find this. So let's have a look. Right. So 5F36 is D. D is OAOD is one of the carriage return. New line, if you like. So anyway, let's have a look at the disassembly for 56B7, or just before it, and we can see that there is something accessing that memory address, and it's doing an EOR load accumulator. I don't think that EOR is right. I think it's probably something a little bit before that, but the BD is correct, the load A with that memory address, coax indirected. Indexed rather, sorry. So we're going to have a look for something that calls into, references that again. 56B7 is definitely. So we're just having a look at the disassembly here. See, there's the loadx, A2, loadx immediate, and then load accumulator index with 5F36. Then it does a JSR to 5D-E5. So there's definitely what looks like some valid code here, still referencing what looks like the machine code monitor register text. Can we see where the start of that code actually starts in memory? See if we can identify a really good code start. I can see what looks like some code. 5500. Unfortunately, this is starting on a page boundary, and just before it is 0, so it looks like some of the code that might have been the machine code monitor has been overwritten by previous data coming in and then hitting into the code that might have been left for the machine code monitor. So I don't think that we've got a full machine code monitor here. Whoops. I'm just having a look. So 78 is set the interrupt flag, and I'm looking to see if usually set interrupts is used for the start of code. You can see here there's set interrupt, and then it does 314 and 315, which is the 0 page or extended 0 page IRQ vector. It's not the high memory IRQ vector. This is the one that the kernel code calls. So the high memory IRQ vector is then calling into kernel code, and then kernel code calls the extended 0 page vector. The extended 0 page vector of 314, 315 is available when BASIC is around and running, or when the kernel is mapped in and running. I mean, the kernel does some extra checks to see where the interrupt has come from, and then redirects to the appropriate vector. Also, the IRQ vector all the way up at the end of memory, the top end of memory, is usually mapped in kernel. So there's no real way of changing kernel because it's in ROM. So that's also why the extended 0 page at 314 and 315 in hex is available for the user to actually extend. So I don't think we're going to find much usable code. I mean, we've got, you know, set interrupt, blah 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 blah. This looks like code, but not code. Looks like data bytes that disassemble to be approximately code and then doesn't. I mean, and indirected with 81 0 page and X is an unusual instruction to be using. And you know, there are break instructions and stuff like that, so I don't think. There's rather a lot of 78s here. This tends to indicate to me that it's data in the portion of memory at 6,000 in hex onwards. This portion of memory is definitely clear. There is nothing there. It could of course be referencing the basic ROM, which is normally mapped in at A000 in hex. 8,000 if you like. 9A is the TXS instruction, which transfers the X register to the stack pointer. This is also a common instruction to use when you are setting up or clearing the stack, or allocating the stack if you like. This is also commonly used during initialization, so the first thing to do would be normally to set the interrupt, then load the X register with FF, which is 255 in decimal, and then transfer X to the stack pointer, therefore allocating all of the stack for your own internal use. That's the usual way of initializing the clear decimal. Also is also a standard instruction that tends to be used because you want the decimal flag to be in a known state. When I'm looking at all of this, I don't really see what looks like good kind of like standard initialization code within any of the memory area that I think that the monitor, machine code monitor, would have resided in. So at this stage I'm becoming less hopeful that the machine code monitor, assumed machine code monitor, is intact in memory. Less likely. 5FC5, 5FC3, RTS. I don't think we're going to find the machine code monitor. I don't think we're going to find enough working code for the machine code monitor, for the assumed machine code monitor. Let's put it like that. So, loading Hawkeye, the main game now, we can see that the Mixi load sprites were there in memory animation frames. In lower memory, we can see that this bouncing message is actually displayed as sprites, expanded X sprites anyway, X expanded sprites. There's a few ways of doing this screen. You can either use sprites, as they do here. We could do an FLD, which bounces a text screen, or we could scroll the text screen using the vertical scroll registers and updating a character set, or the character screen rather, data. I might have used an FLD. Using sprites is actually probably a lot, well, it is a lot simpler. An FLD requires more precise timing. FLD, a flexible line distance, which is where you force the screen downwards by forcing the VIC into a particular state where it inserts blank lines until it actually starts rendering the character lines. slightly more precise timing. It's not overly precise. I used an FLD effect actually with two FLD portions of the screen to bounce the flip disk message in Tusari, the disk version. And actually that flip disk message with an FLD effect and also horizontal scrolling was directly influenced by this flip the disk to side 2 message in Hawkeye. The FLD effect that I actually used in Tusari was actually a precursor to implementing vertical parallax scrolling, if you like, where FLD was used for that. It was the first ever effect used in any game on the Commodore 64. So I'm just looking through the memory here, looking for the title screen text. Actually, the title screen text, you can see, is actually split up into a few different areas. So we have the logo portion, which uses a particular character set. We have the bottom portion of the screen with the larger zooming in text, left and horizontal scrolling, left and right text, is actually from a different portion of memory. We can see how in the second screen bank it's actually building up the text, and then the top left screen bank, the first one, actually moves in the portions of the text horizontally. So it pre-calculates and then scrolls them in. This is the high score table display. So we can see where all of that is allocated within the memory, within the graphics memory. Character set is at C000. So actually the character set and the screen being displayed for this large text at the bottom of the screen is actually using the same chunks of memory, if you like. And that's the great thing with the Commodore 64, is that you can use the same memory for the screen, but you can also use the same starting memory address for the character set, and then the video decoder will just decode the data as appropriately. So if you don't use the first X number of characters, then you are free to use that for screen data, or vice versa. If you want to use the first characters, then you can use the next screen up. So we can see here that the message, the SLF system online message, is actually dynamic sprites. We can see that the first sprites in the last VIC bank are actually updated when the sprites animate, and it copies those from lower down in memory. You can see that the green copies are happening when the player character runs around and everything like that. This is a way of getting around the problem that it's not really a problem. I mean, there are 4 character sets for the parallax scroll. You can see the 4 character sets there in the last half of the sprite memory mapped out. So, and because you don't want to really have to copy across a whole bunch of animation frames for different animation frames for the monsters, the more efficient, cost-effective way of implementing this is to copy across the animation frames for the player character from somewhere else in memory. We can see if we start the game again, if we start the game, look up in the left-hand corner, we can see that the stretching, kind of like compressing sprite effect is actually just dynamic sprites, where it just copies across the lines that are needed. That's certainly one way of doing it. It's probably the easiest way, because you don't want to try and use sprite stretching techniques to do that, when you can just copy across sparse lines of the sprite instead to do the teleport in effect. Now let's have a look at the parallax scrolling screen. We want to have a look at the screens that are displayed. And now if we have a look at the different character sets, because we've got 4 known character sets, we can see them mapped out. Well, these are character sets for the title screen. Lower down in memory, might be copied over. Now, we can see that the two screens are double buffered, so we've got at least two screens for the game. Now, when we switch between the different character sets that are used, the 4 different character sets, you'll notice the background shifts left or right by 2 pixels, depending on which character set is used. That means that we have 8 pixels horizontally for a character, but in multicolored mode it's divided by 2, so we have 4 different states, 4 different X scroll values that we need to use. The main screen scrolls in 2 pixel high resolution pixel chunks, so that means we have 4 character sets. Now, the character data for the parallax effect is static, so when the screen scrolls left and right for the level, the background character sets are static. You can see that the actual characters that are used don't change, it's just the foreground characters which change. Now, when the character sets are rendered with different horizontal pixel scroll values, this means that even though the foreground level scrolls with pixels, the character set counteracts this pixel scroll. It works in the opposite direction, and that means that then the background parallax layer stays static. It's a really cool effect. You can see where the get ready message comes into the screen as well, so there's quite a lot of updates in these screen banks for visible messages and stuff like that. But this parallax effect, even though it uses a lot of memory for the 4 different character sets, looks really cool. And this effect really inspired me to try and do similar effects as well in the games that I was working on at the time. Now, the first few sprites are dynamic sprites. You can see that dynamic sprite data actually in the first few character rows of the screen, because the screen here, the top left screen, is at C000, but the top of that screen is actually this score panel, but it's rendering the score panel, the VIC is rendering the score panel from a completely different area of memory. So that memory for that top left hand screen, the first screen, is actually just not really used. So it can be reused as dynamic sprite data. That's really quite clever. So the score panel there is rendered from a different place in memory. The double buffered screen for the main game portion can then be reused, which is a very efficient way of reusing your memory. There's actually a similar portion of dynamic data that can be used for the sprites there, and actually if you have a look in the sprites list, I think that's using the explosion frames for the next row down in the sprites display. I think that's probably that. The level completed message comes up in that part of memory. It's not doing any loading right now, but when I press fire, when it scrolls, oh, whoops. Let's try and complete the level again, but not in demo mode. When I'm firing the weapon, if you look in the currently being rendered character set, you can see that there are a couple of dynamic characters which are actually copying the background character that's being used and then masking in a bullet effect and then using that character. Now this means that I think the game updates a maximum of 2, maybe even 3 dynamic characters. I think it's 2. With the bullet or the laser effect or whatever that's currently being used. This is a really good way of having nice character-based weapons effects that don't have the usual kind of like black border around them. Now the level intermission screen you can see is loading data. There's a whole bunch of writes going on in the background there. The graphics data for the level hasn't been updated until it decompresses when it displays this warping to the next level name message. Now, for the parallax for this level, you can see that it makes use of a dead space or black character, or a 0 character if you like. So scrolling, again, choosing the different character sets shows the pixel offset scroll, but you can see that the mountains use a lot more detail in the characters, but then there are these at characters, which is character 0, which shows that there's a lot of dead space or black space there. So when the character set, character scrolls across. These mountains horizontally scroll, but they scroll into what is like dead space. So when they scroll into black, you don't have to update all of the characters to, well, you don't have to use all of the characters to contain the detail. It means that you can pack a lot more detail into just the things which are visible, in this case the mountains in the background, so the mountains can contain a lot more detail, and there is a lot less, if you recall in the first level, the parallax effect were basically vertical columns repeated across the screen, which looked a bit repetitive, to be honest. The graphics here, the background mountain graphics here, are a lot less repetitive because the data can be included in the mountains itself, the detail can be included in the mountains itself, so you get a lot less repetitive pattern, which, to be honest, looks a lot better. I think it's a trade-off. You either use quite a lot of dead space or repetitive space in the background and then have this vertical repetitive effect, or you can include a lot more detail but having dead characters. The cost function here is basically on how much or how many characters you can allocate to your background parallax layer compared to the number of characters you want to use for your foreground layers. For the weapons effects for the main foreground character set, for example. So there's a trade-off here in the memory that you want to allocate for each effect. We can see animation frame data in the title screen for the mountains. The animation frames for Hawkeye standing on top of the Thalamus logo, for example. The sprite frames for the effects, music, demo, and then the X icon to cross out or to disable this option. These options are changeable, I think, by pressing the function keys. Anyway, you can see that the Hawkeye standing sprite graphics use a few different sprites overlaid on top of each other to get the appropriate effect with the appropriate colorization that they want. Bear in mind that background here is transparent with the raster bar effect. The background is not black. The background are the cycling raster bars. Thalamus logos here for the sprite. We can see on the character screen, debug character screen, that there are no Thalamus logos. The Hawkeye is not standing there. We can see that the sprites here are the mountains that are behind the Hawkeye logo. So we have a few sprites on the screen, at least 1, 2, 3, 4, 5, 6 for the standing Hawkeyes and the Thalamus logos, and then we have the sprites in the horizontally scrolling mountains behind the Hawkeye logo itself. So we have more than 8 sprites on the screen. Definitely more than 8 sprites, because we've at least got 1, 2, 3 sprites for the music effects and demo mode, and then if all of them are disabled, then we have another 3 sprites for the X sprite, the cross out, the red cross. So that would be another 6 sprites. So there's definitely some sprite multiplexing going on in the title screen, kind of multiplexing, naive multiplexing, if you like. It just that there is probably no real sprite multiplexer there which deals with sprites crossing between boundaries. It's just set boundaries that don't change as it goes down the screen. The sprite register updates are just updated as the raster progresses down the screen. So that if you like, naive or simple sprite multiplexing was actually the basis of the multiplexer which I used to sell in C64 classified advertisements, actually, and I used to have quite a good bit of pocket money being made from that. Eventually I sent it to Commodore Disk User, and I think they published it in one of their issues, and they sent me some pounds as publication fee for that. So let's have a look at the disk image itself, the files on the disk image. There's only one extractable file on side A. hits the auto boot file, we can see that it starts loading at 0326 in hex, and then we have probably some vectors, and then we have the code itself. Again, look, starting with 78, which is set interrupt, and then A2, etc, etc, A2, 8E, these are opcodes. So I'm just using a more up-to-date Vice emulator at this point. I'm not using ICU for this portion of the debugging. I just like the shortened BK command in this version of the Vice monitor rather than having to type in BREAK break all the time. So you can see here that the auto booting disk loader starts at 334, set interrupt flag, load X, blah blah blah. Does a whole bunch of what looks like a mixture of self-modifying code, quite a lot of self-modifying code. It's probably modifying state within the code as it's progressing. There's some kernel functions that it's calling into, so we'll have a look at those kernel functions as well. These look interesting. These ones are from memory, file related functions, and file handle related functions. So we'll have a look at these. We'll put some breakpoints so we can actually see what the registers contain at the various different execution points, I think. What we can do is that we can put breaks up at the high portion of the kernel, and we can see when these high portions of the kernel are jumped into. We can see that they're being called from 48C, for example. JSR EDDD at 470 in hex is interesting. FFBA. Can anyone remember what FFBA is? Anyway, FFBA, which is there, that JSR, is... I can remember. This is just for everyone's benefit. It is set LFS, the set file parameters. Logical number, device number, and then the secondary address. FFPD is set file name. What are the registers when it's doing the set file name? X and Y. I think it doesn't care. It's setting a 0 file, right? A was the accumulator, which is the file name, length 0, right? So it doesn't really care what was in the X and Y. So actually, it was opening a 0 length file. These are all serial port functionality. There we go. It's setting up it is setting up an address in 9E9F for the indirected load at 41A in hex. 4A3 is actually the break instruction there at the moment. EDD. So I think we can probably guess what EDD is going to be doing. It's doing a bit with 9.4, which is what, going to be the output character or something like that on the serial bus. Let's double check this. I have a feeling it is going to be output byte on serial bus. Interesting. So it's actually sending raw bytes to the serial bus. What? I need coffee. What raw bytes is it sending on the serial bus? Well, let's have a look in memory, shall we? I have a feeling it's loading from 4A1 indexed with Y. It's restoring the Y register. It's doing an RTS, which will take it back to, there we go. This is reverse in memory, so it's MW command, which is memory write. And it's memory writing to the disk memory, starting at 500 in hex, which is one of the disk buffers. Interesting. So it's doing a memory write. RTS here, so it's finishing the memory write command. So the memory at 4A7 that it's now sending over, which is, 9E9F was 4A7. So this looks like drive code because JSR 6A3 corresponds to the memory at the internal drive buffer memory. It's a free buffer. There are several free available buffers in the drive RAM. And that memory address corresponds quite nicely. So I think this is sending now, with the memory write command, drive code. So the code that is currently in the Commodore 64's memory some of it is being sent to the drive to execute as drive code. We can see at 4B0 in the Commodore 64's memory, there's a store A with 1800, which is, the drive's version of the serial interface adapter, complex interface adapter. The CIA chip, basically. So it's the equivalent. I've forgotten what it's called. It'll come back to me eventually. But anyway, it's the chip which helps to interface the CPU on the 1541 with the external world, with the drive mechanism and so on and so forth. So anyway, yes, this looks definitely like drive code. And now, what is it doing? Well, it's doing some more self-modifying code. This code, there is a lot of self-modifying code in this. It means that once you map out one function, the functionality of that function can change. So it's doing the same kind of thing again. It's opening another zero-length file. It's then sending information to the serial bus again, but this time the information that's being sent to the serial bus, not interested in jumping into the vector because I know that it's kernel code. What I'm interested in is to see when it comes back to the user code, which it will eventually do. Here we go. So yeah, again, setting the file parameters, again setting the zero-length file name, again opening the file, again doing a checkout, which is defining the file as default output, blah blah blah. It's advancing through the memory address indirected through 9E9F. It is incrementing the chunk of memory it's going to read with that indirected load accumulator with bracket 9E indexed with Y. This time it's doing a memory write rather than a memory write again. But this time the memory write looks like it's writing at a different memory address, starting at in a different memory address in the internal drive memory. Perhaps we'll see what it's doing, just to really make sure. Okay. All right. So yeah, 9E9F. Again, in advancing the indirected memory address pointer, advancing through another chunk of memory, more self-modifying code. Again, remember it's in reverse order, so M-W and then low byte, high byte, if I'm reading it backwards. So it seems to be sending 10 in hex, which is 16 in decimal, 16 bytes of data in chunks to the drive's memory, and it seems to be doing this repeatedly with incrementing memory addresses. There are different ways of getting code into the drive's memory. This is reading data from the Commodore 64's memory and then sending it over to the disk drive. One way. The other way is to have the drive actually read data from a certain track and sector into the drive's memory, and it will store that data in the buffer. That's doing an explicit block read command, I think it was. The third way of doing it is to rely on the drive's internal behavior to have that data already in the buffer if you do a normal file access from the Commodore 64 side. So if you do a load file, of course the drive needs to load this data into its internal buffer and then decode it and then send it over to the Commodore 64. So if you rely on that behavior of having that memory initialized with the file data that you've last loaded, and here you can see that the memory write command has been updated again to point to a different memory address. Gosh, it's doing this in 16 byte. If you rely on the memory state of the disk drive to contain the particular file data in a particular place in its internal RAM buffers, then you could just do, if you wanted to, you could just do a memory execute of that, relying on the behavior, the expected behavior of the drive to have this data in memory. So that's the other way of doing it. You know, if you wanted to, you could make it really quick. Now we can see here that the command has finally been updated to be an ME, which is memory execute, and it's doing a memory execute with 6E0 in hex, which I think it is, unless it updates it again in memory before sending it out. I think this is where the start address for the drive code is. So what we'll do is that we'll open up another disassembly view right now, and we'll set the disassembly view to be the drive. And well, currently the disassembly view is for the Commodore 64. If we step one step, we can see that the drive disassembly view has updated with the drive's program counter, and currently it's using the drive kernel code, so it's executing the drive's kernel. That's no problem. Drive code inside its ROM. But the memory execute is going to be called, and then the drive will dutifully execute the code which has been uploaded by the Commodore 64 to its internal buffers, and that's when we know that it's starting to execute the drive code. And there we go. Now the drive is executing, you know, currently the program counter is at 6B3. So it's advanced, it's executed for a little while before we've hit the next breakpoint, and that's perfectly fine. Now we can see that the Commodore 64 is setting these flags into CIA 2 at DD00. It's doing a branch on minus to 3F5. It's doing a bit test with D011 in the VIC. Of course, doing a branch on minus test for D011 in the VIC is just looking for the high byte of the raster position. It's just basically checking for the raster being off the bottom of the screen, or off the top of the screen, depending on your point of view, but basically it's a raster position which is off the screen. We can see a little message here. Mario Van Zeist, MVZ, I think it is one of the coders' names, 1988. Boys Without Brains, load. Oh, I remembered Mario's name correctly. Oh, that's great, Mario Van Zeist. I don't know if I'm pronouncing it correctly. I hope I am, Mario. I'm sorry if I'm not. So the drive code is doing a bit test with 1800. Drive code is waiting for a signal from the Commodore 64. What I did there is that I waited for a write to the CIA2, basically to see when the Commodore 64 started sending a signal, hopefully to the drive over the serial bus. Serial port, rather. Once you start writing drive code, you can, if you want, to completely take over the signals on the serial port, and effectively there is no serial bus anymore if you use the signals differently to how they're set out in the bus standard, of course. If you use a 2-bit protocol for the transfer, which we looked at in a different previous video, then you get a quicker load, but you break the serial bus protocol standard, if you like. So you hope that no other devices are connected to the serial port, because if they're listening to this, they might get a bit confused about what you're doing, because you are no longer following the serial protocol. You're interleaving the signals in different ways, which it wouldn't understand and wouldn't expect. So hopefully they're not listening to commands. That's actually why I think I would use the ATN signal for resetting the drive code and exiting the drive code. So if my drive code found that ATN had been asserted, then it would immediately quit and it would stop. This meant that if the Commodore 64 was reset and it issued an ATN, it would reset the drive code in the Commodore, in the drive itself, and then the drive would be ready to talk normally via its normal serial bus protocol, which is a nice friendly way of doing it, rather than just making the drive have to be hard reset at the same time as, you know, hard resetting the Commodore 64, or even soft resetting. So we can see here that the drive code is doing the usual kind of thing, waiting for signals from Commodore 64, checking to make sure that the right signal has been set with this handshaking model. Looks like a handshaking model. Code is, obviously code is different. Sometimes it's really easy to spot a 2-bit protocol, 2-bit transfer protocol, and then sometimes it's not. Like in the previous video, the 2-bit transfer protocol was incredibly obvious to see. There were 4 chunks, 4 practically identical chunks of code for each byte that was stored. So that's obviously a 2-bit transfer protocol. So you can either let the drive send raw bytes over the serial port, and those bytes are already decoded bytes, or you could, in theory, I suppose, if you wanted to, but it would be quite slow, wouldn't it? You could send over raw GCR encoded disk data, I think, and then decode that on the Commodore 64. It's an interesting idea, but probably really, really slow. Not what you would want to do. So, you could have a turbo loader, I suppose, which does a minimum amount of decoding of the GCR data and then squirts it over to the 64 for final decoding. That might work. The limiting factor here is not really the bits that you're sending over the serial bus, a serial port rather. It's actually the time taken for the drive to decode the GCR data. Because in group code recording, the limiting factor here is not the bits being transferred over the serial port. It's the time taken for the drive to do all of the quintuple decoding to nibbles, which is 4 bytes. It's 4 bits, so 5 bits to 4 bits decoding. It's quite time consuming, especially within the limited memory constraints of the 1541. Offloading that to the Commodore 64 or sharing the workload might be more optimal. It would also make it really interesting to try and obfuscate slightly the code that is, decoding the bit data coming from the 1541. So the 1541, when it decodes GCR data, it needs to do several passes. It needs to read the data from the disk a few times to allow enough time for the 1541 to decode the bytes to send them back over to the Commodore 64. So now this is doing a whole bunch of tests with expected data coming back from the 1541 by the looks of it, and it's doing a final store here. 32B9 is actually storing up through memory. We can see that it's doing the bit tests here. 1, 2, 3. So it's merrily advancing up through memory, just doing all of these stores. And then eventually the RTS comes into play. The drive code is still running its, the drive is still running its drive code. And there we go, it's jumping into 810, which is that it's not a frozen. I mean, it's not really a freezer because it decompresses memory and then it jumps into the game's start address nicely. So, or rather, it just relocates data nicely and then jumps into it. So it's not really a frozen code. It's just moving memory or decompressing and then running the game's entry point. So it's something which can be started with the basic sys command, but it's it doesn't have to do that. Actually, you don't even need the sys at all, obviously, because the boot menu loader code was just calling the code directly. There we go. It's just running the Mixi load now. It just did all of that copying and everything, and then just displays this screen. The drive code is running, sending bytes back to the 64. We can see here it's still executing the drive code. See more self-modifying code which updated the indirect jump address at C8D2. Seriously, more self-modifying code. All of these parts where it updates the self-modifying code, first it's obfuscation. It increases the amount of time taken to reverse engineer what the loader's doing, and it's a little bit of protection. And secondly, it basically relies on previous code state. So if somebody decides that they're going to alter the code to try and hook into it in some way, it self-modifies the code, either by incrementing or decrementing a memory address or changing the opcode. And it means that any attempts to modify the code, or some attempts to modify the code, will result in unexpected behavior as it's changed the address. Sometimes it uses the code as a decryption key. Sometimes it just relies on the previous state of the code. And if that state, the end state, then changes, then of course the code won't run as expected. So it's actually a double protection method, if you like. One, obfuscation, and two, relying on the correct state of the unchanged memory, or rather, the code relies on the code being in an expected state, and if it's changed from that expected state by hacking attempts, then it will fail, or it could fail, or it increases the likelihood that it will fail. So here I'm just saving all of that memory so that it can be inspected later on. At this point, I'm kind of assuming that the previous state of the 64's memory is going to be irrelevant at the particular point in time when it wants to run the code at 810. Okay, because 810 is basically memory moving around and decompression code and everything like that. Again, it's not really frozen code because it runs nicely into the game's entry point. It's not some freezer cartridge produced compressed self-extracting file which attempts to restore all of the I/O state and everything to a known state. The game code practically doesn't care what the previous state is because it initializes all of its state correctly. So I saved out all of the screen data as well from 0400 and hex onwards, just to be on the safe side, but I don't think this code relies on that. This is the basic sys entry point. And of course, the basic command is not really used because, again, the code just jumps straight into 2064 in the decimal, which is 0810 in hex. It just jumps straight into there. We can see that there's actually quite large chunks of empty memory. Maybe I've saved too much memory. That's entirely possible. So these empty chunks might be music or bitmap data or whatever. That's perfectly fine. Doesn't really matter. What matters is that there is enough memory saved out for the self-extracting code to actually, and you can see here it's just doing a whole bunch of, let's take code and then relocate it to 0 page way down, and then let's take data and then relocate it in indirect and maybe decompress, blah blah blah. Not really that important. What is this doing? It's doing some rotates. When it's doing code like this, when it's doing rotates, it seems to be extracting bit values. If it's doing that, then it might be doing some kind of like decompression with a flag saying do this. Maybe it could be a variant on RA, it could be a variant on LZ compression, it could be some other compression, right? Don't really care at this point what the compression algorithm is. Looking through the memory in the ICU debugger, it didn't seem to be very well compressed, to be honest. There seemed to be quite intelligible data. If it compressed really well, then the data would not be that visible. But there looked to be kind of like sprite data and stuff, kind of, I suppose. So anyway, not really interested in the compression method. We're just trying to find out where it calls the game entry point. Here we go. What's it doing here? Well, there we go. That's the JSR. And this code seems to be doing some VIC initialization, some VIC register initialization, high memory initialization. This code does look a little bit freezer related because it's doing a whole bunch of, initialize top memory, initialize VIC state, initialize blah 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 blah, initialize color RAM as we go down, initialize all sorts of things. But it runs straight into the game's code, so maybe it's game code initialization, which is really nice, and just comprehensive. Maybe they're just doing that, perhaps, because it doesn't look like it's doing a full state. Yeah, it's not doing a full state retrieval. It's just doing what you could call standard initialization code. So it's just, it's game code rather than freezer code per se. Freezer code would tend to try and restore CIA 1, CIA 2 state, color RAM state, VIC state, SID state, and it would try and restore that from stuff which is being stored in memory rather than to default clear values. And it would then try and avoid it would then try and restore lower 0 page state and upper 0 page state, and do that final restoration while sitting in probably the lower area of stack. So anyway, this looks like the standard game initialization code. Yeah. So it looks like it's getting into the game code at this particular point in time. No problem there. There we go. And it's just displaying the bouncing sprite message for inserting side B, so we know that we're definitely within the game code at this particular point in time. So here there's the file name, save file, disk error, char 12, col 12, lev 12. This might be code which was left over from the level editor, right? Level 12, char 12, column 12, disk error, file name. Interesting. Might have been the level editor code. There might be some level editor code left hanging around, I suppose, or animation editor code, perhaps. I mean, there's other code left hanging around inside the monster show memory. The machine, what looks like machine code monitor related code and data. So maybe it's entirely possible. The sprite data, though, you see, the sprites are actually in what looks like in the lower bank, right? There was this memory here, which looks like basic memory. I put 48 00 in hex. This was just before the what looked like the machine code monitor memory. So what we're going to do at this point is, I think it's easier to transfer this memory from 4800 in hex to 0800 in hex, which is the default start of memory in BASIC. Okay, so because we don't want to have to update the BASIC start addresses and stuff, so I'm going to use, the standard old restore basic program poke and sys. There we go. 2050 is this byte here, 08422291, and here we go. So we've got what looks like the start of a basic program with v equals 53248, which is D000 in hex, which is the VIC address. But there isn't too much of this basic program, so that's all there is for that. It's an incomplete fragment of basic program data in memory. Not really that interesting. But it does show that there is, there are fragments of data inside the monster show. I suppose in theory it means that the monster show could be compressed down into a much smaller space. And I wonder if the monster show that was included on Zap Megatape actually includes all of this extra superfluous data as well. So now we're going to have a look at the original tape as it was released, and we use the tape tool to have a look at how it loads, first of all, or how it would load, and it's going to use the restore IRQ vector trick, and it's going to jump into 2A6. That's what the tape tool says. So let's check. It loads data at 29F, and 29F is the IRQ vector restore value. Well, no, there is an IRQ. There's a test for restoring the IRQ back to what it was, and then it causes the tape routine to exit out and then call into the vector to actually call the code. So that's what it's going to do. We can see when it's loaded the tape header that it's of course loading data at 29F in hex in memory. We can see that there's a whole bunch of data in the tape header, but it doesn't look that sensible right now. Obviously kind of either random data, which I don't think it is, or encrypted in inverted commas. Probably just an EOR. Let's have a look at what the code does as soon as it starts running the auto load code, and here we are. Well, there we go. Quite expected. This OR A instruction, indirected with Forcian X, can be, ignored. It doesn't actually do much apart from update the accumulator and of course read the indirected memory address, but we don't really care about that. What we really care about is that the real code start is at set interrupt flag, which stops the interrupts, except non-maskable interrupts, of course, but Anyway, at this point, this is where the code tries to take over what the Commodore 64 is doing. So it's going to E544 inside the kernel. Does anyone want to have a guess what E544 inside the kernel is going to be doing? It initializes the screen, clears the screen, basically. Color RAM and screen memory update, as you would normally expect. Just using indirected addressing, and that's because, let's see, current color RAM location. That's because the kernel routines rely on some calculated color RAM and screen RAM addresses. In theory, it actually makes it so you can see that the screen has been cleared. In theory, it makes it really easy to redirect the screen routines to elsewhere in memory, of course, because you can just update these values and then have the kernel operate within those values. The screen that the kernel thinks it's updating doesn't have to be the screen that the VIC is displaying. They can be entirely different. This is starting to update the cyberload message and bar effects and stuff. Oh look, we can see some EOR code with the data that was loaded in the cassette buffer. Oh look, the cassette buffer has been decrypted. Now this is running some rather interesting garbage code. It's not interesting for what it's not doing, it's interesting because it's running garbage. Why is it running garbage, you may think? Well, it's part of the protection. It's part of obfuscation. While the person who is trying to reverse engineer this loader is looking at this code and thinking, well, what on earth is it trying to do? There is something which looks like a branch unequal to 400. However, this is also a red herring. What we do have is we have a store A with F55 again. Quite puzzling. Why would it be trying to store into kernel? At this point, we're going to think, hold on a second, what code is it actually going to be, like running outside of this loop of garbage code? And how does it get there? So we use an area break at this particular point in time. Well, we can see that, or a ranged break, if you like, an area of memory, a memory range. And we can see here that it's gone into 351. This is interesting. And now this is doing some CIA updates. So at this point, this 3BF function is doing tape bit arrival checks, and then it's doing checks with the timer value. It's updating the scroll position for the cyberload bars, so the character which scrolls across, moves across. It's not scrolling, it's moving. The reverse space, or the space character, basically. It's updating that. It's doing a CIA1 timer value check to decide on whether or not, I think, what it looks like is doing a check to see if the tape pulse is long or short. Basically, it's checking to see if the timer has... completed. If the timer has completed, the timer value will read the same. If it hasn't completed, the timer value will be different. And it sets or clears the carry flag appropriately based on the width of the pulse from the tape unit. If you are reading different pulse lengths from the tape unit, then you can decode whether or not you mean a binary 1 or a binary 0, for example, when you are shifting values into an accumulator for the real byte value that you want to decode from the tape. Or, say for example, you could try and count a certain number of specific pulses of specific lengths to detect whether or not you're at the start of your file data. See, it detects the pulse on the flag pin, which is the cassette tape. Did we get a signal on the flag pin from the cassette unit? Yes. Or no? If no, then it goes back and checks. If yes, it checks the timer value. This is kind of like one of the standard ways of decoding bits from the cassette unit. You can either read the flag signal level on the cassette device directly, or you can trigger an interrupt to happen, which then runs code, and then that interrupt code can then check the timer value. You can do it either way. I think, to be honest, the interrupt triggering method is a little bit more accurate, but it takes more setup code, and the cyber load needs to be really, really small. So doing it without an interrupt and just checking the bit value directly is also perfectly valid, especially when you have code memory constraints. And with the cyber load, most of the message saying cyber load now loading Hawkeye, blah, 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 that's a lot of bytes. It's what, 36 bytes or something like that, and 36 bytes is 36 bytes of, that is not being used for code. It's text. So yeah, there are trade-offs here. You can have a nice pretty message, but you have much less code space to work with, especially if you want your auto-booting tape turbo loader to have good functionality if you want it to load quickly. Anyway, so what this is doing is that it's decoding bits from the tape now, and it's decoding that as bytes. It's updating what looks like a checksum into EF, add with carry store EF, and then PHA, PLA, saving and restoring the accumulator value, of course, because we want the accumulator to return the actual byte which is being read from the tape. And the byte which is being read from the tape is then checked with known values. It's looking for specific bytes coming from the tape to indicate that your file data is the real file data and not some, randomly read data from the tape. Okay, so this is what it's doing. When I did my tape turbo loading routines, I used to have like a shifting sync test first, and I actually had, to account for different bit pulses being read from the tape unexpectedly between transitions of files, stopping and starting the tape motor would sometimes introduce a pulse when you don't want it. I used to have a constantly rotating and shifting byte, which I would check for a known byte value first and a known bit pattern. And then once I got that bit pattern, then I would use that as the bit inside a byte synchronization check. And then I would check for the file bytes. And if that check for the expected file bytes at the beginning of the files check failed, then I would revert back to the cycling byte method to try and pick up the correct start of data. So, FFD5 is doing a store, it's not doing a JSR, but the FFD5 is, load. Maybe they're just storing it there just to be like a red herring again, to try and obfuscate, or maybe they're self-modifying the address. Look, they're self-modifying. Yeah, they're self-modifying the address that you're storing to. So, okay, so 394 increment. Yes, see, so actually instead of FFD2, it's obfuscating where it's storing the cassette code, and it's actually storing it at 0002, which is way down low in 0 page, but it's storing it with an absolute address rather than a 0 page address, but that's fine, it's still storing it in 0 page, just above the CPU pot, which is at 00 and 01 in hex. So yeah, look, it's pulling the accumulator, blah 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 blah, storing, incrementing, branching or not equal, incrementing, branching on carry set, blah blah blah. So as long as carry is set, it seems to indicate that there are bytes available during the tape load, and it keeps on storing, probably until it gets to 39F, which indicates that it's reached the end of the file that it's detected, during the tape load. Looks like the compare with EF is comparing then it loads another byte from the tape, and then it looks like it checks. That's the checksum basically. It looks like it checks the byte loaded from the tape with the checksum that's calculated in EF. FCE2 kernel function. Does anyone remember what this one does? We don't want that to happen, do we? No, we don't. So we're putting a whole bunch of breakpoints. We're going to see what happens here. Loading, loading, loading. Stop. Oh, look. It's now a jump with 3AE. So it doesn't compare. It jumps straight over. Interesting. And look, the store A, which was storing in low 0 page, is now 3A7. So it's been self-modifying some code. It's loaded a whole bunch of data, which eventually has changed the JSR, which does the checksum check, to a jump, which jumps to the checksum check, and then the checksum check RTS will return. That's sneaky, and it will return with whatever has been stored in the stack. Even more sneaky. Okay. Self-modifying code loaded from the cassette into its own tape turbo loader. Ooh, nasty. So, loading self-modified code from the tape onto itself is another really good way of obfuscating and doing this protection check. It makes sure that the code that you want to execute next is not being modified by anyone trying to hack the data that's already in memory for the previous tape turbo loader. So at this point I was beginning to think, oh gosh, yes, cyberload. This late version of the cyberload is actually, quite convoluted in its execution path. I mean, jolly well coded. I mean, getting all of this working and making sure it works without, mature debugging tools like this must have been really quite interesting. Right, look, you can see, how did it get to execute code at 2? Well, it started executing code at 2 because of this jump. You can see here, 3A4 in hex is the JSR to 3AE, which then does a compare with the accumulated CRC. If you think about it from a protection point of view, ignoring the last byte inside the tape data, if you're reverse engineering it, makes it look like, it's not obvious, it's ignoring the last byte. So if you know that you're trying to check for CRC data being correct, it kind of might make you think that your data that you're loading from the tape is incorrect, and you might think, well, hold on a second, where if it's ignoring the last byte, if it's not expecting a last byte because there is no last byte CRC data, it might make your reverse engineering of the data on the tape a little bit more difficult. It might delay you a bit because you would think that you hold on a second, I'm reading the wrong bytes. My CRC is wrong. What can I do about this? It might change the way in which you try and synchronize data bytes by emulating the tape turbo format. Writing your own tape turbo loader which interprets the bit pulses and storing out the data. It might make you think twice about the data that you're reading and whether or not it's correct, and it might make you save out the wrong data, and it might make you take a much longer period of time when you're trying to reverse engineer. Stepping in here, you'll see that actually it goes through several different stages of loading different chunks of data at different places. Over 0 page, over its own code. We'll dig into that now. The first chunk, it seems to finish here at E8. We've already loaded some code at 2 in very low 0 page basically. We've already loaded some code. NMI setup, for example. Look, it's doing an EOR with code that's loaded, or data that's loaded, which is code, and then it's doing an EOR with code which has been loaded in a previous pass, which has probably also been dynamically loaded from the tape as it's also running, which makes it even more convoluted. This loader is getting progressively more evil as time goes on. So it's finished loading up to E8 right now, but we know it's going to load more data. We know it's loading more data because when we look at the memory view in ICU, we can see it's writing bytes at different places, but some of these runs of bytes which it's writing to the memory are actually really quite short. It's loading fragments of bytes, byte data, short fragments like maybe 5 or 6 or 8 bytes at a time in different places. It's really quite convoluted. Very nice though, very nicely put together. Much respect to the author of this particular version of Cyberload. And it only gets more convoluted as we dig deeper and deeper, which is great. It's a fantastic puzzle. It reminds me how hard it was back then to actually try and hack this directly, like way back, without all of these, mature debugging tools and stuff. So now it's updated the data store address now to 100. There seems to be like a byte coming from the tape which defines a delta value to add on to this store address. You notice that it's doing CRC ADC 393 store A 393, which is the low byte of this absolute store address. So it's loaded, if we have a look, it's loaded a bunch of bytes into 100, which is the start of the stack, usual start memory address of the stack, and it's loaded EA, which is NOP, which is the NOP opcode, which does nothing, and it's loaded 8 bytes of EA into the start of the stack. Okay, now it's loading, and now it's been storing, or going to store, data into 200, which is just after the end of the stack, the start of the next part of extended 0 page, if you like. When I say extended 0 page, I mean any address which is greater than the first page of 0 page, which is 256 bytes. So any address which is from 200 in hex to 3FFF inclusive is extended 0 page, basically. The normal basic kernel vectors and stuff like that, and the cassette buffer and all of those kind of things, extended 0 page. Anyway, you can see here now it's doing stores to 2A7. The code at 3A4 is still doing a JSR. Here we go. I'm taking a screen grab so that we can compare it later on, because it really is self-modifying code with data that's loaded from tape onto itself. You see, it loads accumulator with 1. It then loads bits or shifts bits from the tape into the accumulator, and then once that 1 is shifted all the way over by the ROLA into the carry, then we know that a full byte has been loaded. Very standard way of shifting bits from the tape into a byte, which we then test or then store or use in other ways. We can see 33C, increment 393, increment 394. So it's loading, if you like, sparse spans of bytes all over itself and all over working memory. Really quite a clever way of doing it and hiding what you are trying to accomplish, which is basically getting data from the tape and then getting the Commodore 64 to execute it, but in an obfuscated way, which makes it hard to pull the bytes directly off the tape. Very nice. Very annoying, but very nice. You can see it's storing it in 340, blah, blah, blah. We're going to remove that breakpoint. No, we'll put it back again. We can see here that each byte that we load from the tape advances pretty much the cyberload bars, if you like. The animation for the cyberload bars, storing in 34A. We'll just let it run because it's relatively cheap for us to restore the state from the emulator back, or get back to this state in the emulator, right? It's finished loading data all the way up until 392, which is this store. So it's stopped at this particular point in time, stopped storing data. That's what we would assume right now. Now, what is it doing now? Well, look here, it is now trying to update the store address to be another run of bytes, but this time the run of bytes is itself. Store A with itself updates itself. It was probably done like this to make it easier to get the saved bytes to synchronize with what the memory should be at this particular point in time for the execution, because the end result for this execution is to self-modify that JSR at 3A4 to be a jump, if I remember rightly. Store A395, 396, 397, and also because it's self-modifying the store accumulator with an absolute address, it's also obfuscating the fact that it's going to be trying to rewrite this JSR. But because we have a single step debug, I think this time round in this pass, because we have a single step debugger, we should be able to see it get to exactly where we want to get to. 3A1, 3A2, 3A2, there we go. 3A4, JSR to jump. There we go. It's already changed, it's finished. And then, there we go. It's now a jump. Ignoring the last byte. I don't know if there is a byte coming from the tape or not, to be honest. I haven't looked. It's not really important. If it's not there, it just serves to improve the amount of obfuscation. If it's a wrong checksum byte, that also would help to improve the obfuscation for the protection check. Something tells me that there is a byte because it updates, but it might be a garbage byte. It might be any old pulses in there just to really throw off the reverse engineering of the pulses from the tape, right? You could, right? Here I am circling. So 3A4 jump used to be 3A4 JSR. So it gets a byte. Could be junk, could be weird length pulses, could be anything to throw off reverse engineering of the tape. But it self-modified the code to skip over the compare with EF, because it's a jump, it doesn't RTS, it doesn't, but it jumps into so it doesn't RTS, and it pulls the RTS from whoever called, or what is on the stack at that particular point in time. So it ignores this compare with 3EF. It ignores the branch unequal to 400, so it was definitely a red herring. Really very, very annoying. There is no loaded code at 400. Again, the author of this version of Cyberload needs another little feather in their cap, another little medal, which says, I have successfully added extra obfuscation, and it gets to there because the RTS pulls that value from the stack. And of course the stack was, at a particular state. Now it's doing some register increments. It's basically doing a time delay, so it looks like it's skipping whatever is on the tape for a particular length of time. So here we are, it's running the code. And why, at this point in the execution, when it starts running this code at 2, comes from the last position of this blank space within the Cyberload loading bars. In other words, the Cyberload loading bars number of indicates the number of bytes that have been loaded to within a specific range. And this value of y is then used as a delay value. So basically it delays the code with the tape motor still running and the tape running past everything else. It delays for an amount of time which is relative to the number of bytes that were loaded from the tape. What this can do is that it can further obfuscate data which may or may not be stored on the tape at this particular point in time, because the code will just ignore a certain amount of pulses coming from the tape. This could mean that you then try and write a whole bunch of random looking data or pseudocode data or whatever, just to try and obfuscate the final game data before you then try and load real game data. Now, this code, starting at 2, does a whole bunch of timer setup. CIA 2 timers, which tends to deal with the NMI, the non-maskable interrupt. So 1.1 was setting up a particular interrupt to trigger, load the value of the timer, and then start the timer. DD0D. We're also going to get an expected value in DD0D. Once we step, boink, we're storing A3 into it. And then FFB and FFA, FFA and FFFB. It's getting a 3B00. So it's setting up a non-maskable interrupt to point to 3B. Here we go, you see? Non-maskable interrupt. So it's going to run a non-maskable interrupt at the code at 3B, which is a bit. And then it does a branch on not equal to 5.6. So it skips over the code, which it should have been running as a non-maskable interrupt. Great. Yet another thing to worry about. When does it trigger this non-maskable interrupt? How long into the execution does it trigger it? DD0E, DD0F, to do with time of day speed. Okay. And then what is it doing here? It's doing some index register arithmetic. It's doing EORs with data. It's doing data with EORs with data that's already been loaded as part of the previous pass of the turbo load code. It could be data, vectors, code, whatever. It's doing a whole bunch of EORs with that, with index values. So it's hopping around index values. It's EORing with a range. It's doing branch on plus. And then it's storing back into 7.2. Gosh, really? Seriously? Okay. So it's doing multiple EOR passes with different index values, and then storing it back in and self-modifying the code, so decrypting by using EOR, and also a key value, if you like, is the EOR value of memory range values at 314 onwards. So anyway, oh gosh, let's see, what on earth? And it does that as long as y is plus, oh gosh, seriously. So it EORs it with a whole bunch of values and then stores. And then it decrypts. It uses multiple decrypt passes. See, this is the code. Data that was in the cassette buffer, which was then self-modified. Self-modified by code itself and self-modified by code being loaded into it from the cassette. Right. So, yeah. Nice obfuscation. Nice convoluted execution. We can see that it does a dex and a branch on not equal to somewhere. Right. Bing, bing, bing. 72, comma x, indirected with x, 72 plus 8b gives fd. So it's going to be modifying code or data, but most likely code at fd, which is currently clear. Let's have a look. So at least it's clear memory, but it's doing a store. It's loading it, EORing it. Well, it's EORing it. Okay, and storing. Right. See, look, it's taking a value in the accumulator, EORing it with what's already there, EORing it again with something that was loaded previously or self-modified previously, and then storing it after a few passes of arithmetic. You know, just to put the icing on the cake, I would expect this branch on not equal address to be self-modified at some particular point in time as well. You know, just because. Or maybe it's not. No, it does a dex. Branch on not equal, so it's probably just going to skip that by 1 byte and then it will execute at 73. Whatever is going to be at 73 eventually is here. There is an ROL. Okay, well, the ROL is superfluous at this point. I don't think there's any code at 934. I think it's a red herring. Again, obviously, yes, completely clear, memory doesn't care. So here, the real decrypted code changes where the NMI will trigger to FFFA, but it also compares memory at F379 to be equal to memory at F379. That's RAM. The RAM is available. So it's checking to see if RAM has been cleared to a consistent value. So what we can do, and it looks like it was then going to run a whole bunch of code which then killed itself by zeroing out the memory as it was executing itself. So that looks like a check to see whether or not RAM has been cleared with the same value, probably to try and stop, you know, some of the older freezer cartridges would clear memory to a known state, in other words, clear it to all of the same bytes, to make it easier to compress at particular points. So if you freeze something, it can say this memory hasn't been touched, it will zero it out, it will make the compression algorithm a lot more efficient. Because the Commodore 64, when you turn it on, the RAM, due to its electrical nature, will be in a state which doesn't have bytes in memory all at the same value. Some will be zeros, some will be FF, some might be some other different value. The memory is cleared. The memory is not cleared. The memory has a default state of not being. It looks like this pattern: 000 FFFFF, right? If you try and render this with VIC as a screen data or sprites or something, it looks like alternating bars of white and black, for example. Anyway, so that's the default state of the RAM power up, is that it looks like this. So the code looks like it was checking for non-cleared memory, for default state memory, which would tend to stop some freezer cartridges from working, because some freezer cartridges were, back in the old days, clearing memory to be that. So what we can do is that we can test that hypothesis by filling memory with the same value. Okay, and then once we get running, we can see from the CPU history is that it gets to 1010 break. And how did it get there? Well, it got there because the memory, the break vector all the way up at top of the RAM was hit at that particular point in time, and then it jumps to 1010, and then it executes the break instruction again. So how does it get there? Well, you can see it's paused at that particular point in the cyberload. So how does it get there? Well, we can see how it gets there from the CPU history. So we will do a CPU history, and we can see here that it's got there because it's running the clear code, store A2, store A92, store A300, all indexed with Y. And we can see that it's clearing the whole memory with what has been read from the cleared memory that we've set it to just prior to loading the game. So we know that that particular code, which was decrypted, does a cleared memory check, which is yet another part of the protection mechanism of this really very convoluted and well-written cyberload code. Thank you very much, original cyberload coder or author. It's self-destruct code, basically. Normally, don't want that to run. Very clever, though. So going back to the normal execution of the cyberload now, the memory check for cleared memory will succeed. So it will say, hold on a second, the memory is not clear, so let's proceed with the execution. After it skips over a number of FFs which are at that point in memory. It's not going to be clearing all of the zero page stuff now, an extended zero page. And here we are. It turns on the screen again. D011 is the VIC vertical scroll and screen enable. So here we alter the timing value in CIA1, or the timer value. So this probably resets the expected pulse length for turbo loaded data. It then seems to be going to 3BF, which is previously loaded tape turbo load code, which does a tape pulse check. It's comparing with an expected returned byte from the tape of F. Once it's got that byte, it then proceeds with the rest of the normal load as you would normally expect. Keeps on going until it doesn't, or while it keeps on going while it does keep on receiving F from the tape. So basically it skips, it synchronizes on F, looks like, and then skips F for as long as it's receiving it, which you would kind of normally expect, right? I mean, for the tape lead in, not part of the normal tape header, you want to synchronize on something which has a known bit pattern, and then just skip that known bit pattern until you get real data. And then the bit pattern that it then checks for and goes around and tries to resynchronize for is the opposite of the bit pattern that it was synchronizing on in the first place, which again makes sense. You want to make sure that you are synchronizing on the right thing. If you don't get it, that's bad, right? You want to get it. You want to get these expected byte values and to synchronize on those expected byte values. That's what it's doing here. So it's doing a full synchronization check with F and F0. Makes perfect sense. It is interesting to note that that very precise timing loop based on the number of bytes loaded in the previous portion of the tape turbo load, cyber load rather, was done with the screen off, and then it turns the screen back on again. It means that it's doing some precise timing there. It looks like, the tape might have weird data, just to throw off reverse engineering of the tape data. Interesting. Looks like it's doing an EOR. Yep. Okay. Did it store into itself again? No. Okay, not too bad then. It's just storing into very low 0 page now to set up some pointers by the looks of it. So it's loading address pointers into memory. Okay, no problem. So it looks like 2 and 3 in hex are the address pointers that it loads to, and then 4 and 5 are, so it's loading 2 pairs of addresses, looks like, or the length. Yeah, the length. The start address and then the length. So 2 and 3 is the address of where to store. 4 and 5 looks like the number of bytes that you want to, or the length of the number of bytes that you want to load before it does the RTS down at E7. The NMI vector FFFA, it is the NMI vector, right? Yeah, the NMI vector. Is it 3E00? I mean 003E, which is this code, which does an increment with 7.5, PHA, LDA, 7.5, compare it 7.573. What? So 7.3 and 7.5 are portions of code within this obfuscated turbo loader itself. Okay. Which is a little bit suspicious, right? Why is this NMI doing stuff, or potentially doing stuff? Depends on whether or not the NMI is actually being triggered during the normal operation of this loader, because the NMI was based on a timer value. So what we can do is that we can put a breakpoint at 3E and then see what it does. It's updating something to do with this ROL instruction. Well, that's what it looks like right now. What it looks like at the point in time when it might have been executing may have been different. Well, look, it's changing 7.3, which is, well, it's EORing it with B7. So does it trigger? Does it run this NMI? The final RTS will go to the address after BFFF, which is on the stack pointer there, you can see it, which is C000, which is where it starts the next code. We'll get to that later on. The addresses that are on the stack are always the return address -1. I mean, there's CPU reasons why it's like that, but we won't get into that right now. Here I'm just checking the timer A and timer B values to see if they are actually counting down. Still, yeah, they are. Here I'm just validating that at that particular point in time when it executes the RTS at E7, it does get to C00, just to double make sure, which it does. So let's put a breakpoint at 3E and also a breakpoint at C000 and see if the NMI triggers the code at 3E before the code at C000 loads at any point. Oh, and yes, it does. So that means, and it's actually triggered at a point where before the instruction at 7.3 has been decoded. So it's in the middle of this decryption routine. So EOR 314, y, you see, look, y is there. So the bit at DD0B is executed when the NMI gets triggered before the rest of the code is decrypted and also before the code at C000 is loaded. So this means that it's doing a bit check, or rather it's just doing a bit with the time of day value. It's then doing an increment, blah blah blah. So it runs this EOR code. Does it? Does it run the EOR code? Branch on carry clear. No, 4C. Well, okay, so it does a logical shift right of 7.5. Okay. Interesting. Eventually the vector gets changed to be 3E rather than 3B, which means that it's not doing a bit with the time of day. So it's not reading the time of day, basically. EOR is what's there. Yeah, so it's EORing with something which is being twiddled with by the NMI timer as well. So it's altering that opcode, which eventually gets executed. Yeah, more pain and suffering. But at least it's only passing through that only once. It only seems to trigger that once, though. Interesting. So if this NMI doesn't trigger, it won't decrypt this particular portion of memory correctly. The RLL instruction will change to be a store. So this code up here is at C00 is just the mixy load code. Bunch of screen clears, bunch of screen updates, or rather screen memory update. As long as the VIC is rendering from that screen, then it will just show on the screen, of course. Border and screen color updates, okay. Sets up IRQ, sets up NMI vectors. Sets up timer values, sets up some sprite VIC configuration values there, down at C04B. At least this code currently is not trying to hide too much where it is setting up the interrupt and NMI addresses anymore. There is a bit less obfuscation, if you like, with this mixy load code. It's interesting that they set the stack pointer all the way to the bottom of the stack, basically reserving the upper part of the stack for something else. Where did the interrupt come from? If it's a timer interrupt, check the timer underflow flag, or rather, not a timer interrupt. If it's an interrupt that occurred from the tape, then check the timer underflow flag, reset the timer, blah blah blah. Extract a bit length, but using an IRQ this time. Seems to be updating the branch address with a state, so the IRQ remembers its state by using self-modifying code. Fantastic, thank you for that. Also self-modifying code there. Also fantastic, thank you for that. Anyway, C0A2. Yeah, thank you for the self-modifying branch destination. Not making it easy to debug this. We have a couple of suspicious looking stores. Ooh, look. That's fine. Those kind of stores are always suspicious, so we'll put a breakpoint on them to see what they do generally. Notice that the screen is in 38 column mode rather than 40 column mode. D016 controls the horizontal scroll as well as the column mode of the screen. Here it's actually getting into the raster IRQ. So there is a raster IRQ running during the tape load to do the little scrolling message, basically. If you look in the debug view of the screen, you can see that there are characters left and right that aren't visible in the Vic rendered screen. That definitely tells us that the screen is in 38 column mode rather than 40 column mode, basically. It's probably to hide where the raster split is for the scrolling message. The raster split may jump up and down a little bit depending on what the NMI is doing, and also depending on what the IRQ is doing. I would not have done it like this, to be honest. I would have just had the raster check for the scrolling message done outside of IRQ or NMI. It doesn't really matter. It doesn't have to be so precise. In fact, that's what one of my tape turbo loaders does for its scrolling message raster split. It just does it in what I tend to call the main line, which is any code which is not running in an IRQ or NMI. So any code which is not running in an interrupt, regular or non-maskable, is mainline code. Because you can just do a compare with the raster position on the screen. It's not like the code is doing anything else apart from trying to scroll a message and trying to scroll the screen at a particular point in time. Here you can see the Mixie load has now properly kicked in. It's loaded all of the graphics data and everything else. So you can see here the sprites display on top of the bitmap rather than in an open border. The thing is that even in the tape loader, even with mainline code, it's entirely possible to open the top and bottom borders. It doesn't need an IRQ or an MI or anything else like that to be able to do it. And that means that you can leave the interrupts free, or available rather, to handle all of the tape loading for you, and you can let that be as accurate as possible and have the mainline code being slightly interruptible by whatever is happening in the tape loading code. That's probably the better way to architect the whole solution. So you see here actually that the Mixie load code was looking at the raster Y position anyway, and basically triggering the music play and everything else and the animation for the sprites after raster position 128.80 in hex. So while it's doing this music stuff, which you can't hear because I've turned off the volume, but you know, the Mixie load is going on in the background, it's also loading stuff which you can see in the red debug memory view of ICU. It's just loading stuff. So there we have it. Now it's at the Mixie load and doing the game load. We'll leave it there because this is a long video already. If you like these kind of deep dive technical videos into old retro games code, then please let me know in the comment section or by subscribing or liking this channel. Thank you very much for watching and have a great day wherever you are.